All right, let's dive right in. Today, we're going to put on our detective hats and crack a really specific, kind of weird mathematical mystery. See, it's one of those cases where you can follow all the rules, do every single step perfectly, and still end up on the completely wrong path.
So, how is that even possible, right? How can perfect math, flawless logic lead you to a totally wrong answer? Well, that's the big question we're digging into today. And believe it or not, the answer is hiding inside these things called radical equations. So, let's open up the case file.
First things first in any investigation, we've got to identify our subject. And today, we're talking all about radical equations. Yep, the case file has officially landed on our desk.
So what exactly is a radical equation? I mean, it's not just any old equation that happens to have a square root in it. The thing that makes it a radical equation is that the variable, the x we're hunting for, is trapped inside that radical sign. It's stuck in there. You could almost say, that's our crime scene.
And here are just a few examples straight from the case files. Take a look. Some are pretty simple, just one radical. Others have cube roots, and some, wow, they even have multiple radicals. Each one looks a little different, a unique challenge for sure, but here's the secret. They can all be cracked using the exact same set of tools.
So, what's in this toolkit, you ask? Well, every good detective has a standard procedure, right? A reliable method that gets them to the truth every time. And for solving these radical equations, it's a surprisingly simple 4-step process.
Here it is, the whole playbook. Step 1, you got to isolate the radical. Get it all by itself on one side of the equation. Step 2, you eliminate it. And how do you do that? You hit it with its inverse operation. So if it's a square root, you square both sides. Boom, it's gone. Step 3, now you just solve the much simpler equation that's left over. And step 4, and listen up, because this is the most crucial step of all. You check your answer. And we are absolutely going to see why in just a minute.
Okay, let's put this toolkit to the test on a nice, straightforward case. In this equation, you'll notice the radical is already isolated. So, step 1 is already done for us. Perfect place to start.
All right, on to step 2. To get rid of that square root, we do the opposite. We square it. And of course, you got to do it to both sides to keep everything balanced. On the left, the square and the square root just cancel each other out. And on the right, 4 squared becomes 16. Just like that, the radical is gone.
Step 3 is just some basic algebra from here. We subtract 1 from both sides, then we divide by 3, and we have our prime suspect, x equals 5.
And now for that final all-important step, the check. We take our answer, 5, and we plug it right back into the original equation. That gives us the square root of 16, which is 4, and that equals the 4 on the other side. It's a perfect match. The method works. So you might be thinking, if it works so well, why on earth do we even need to check?
Well, here's the twist. It's because sometimes this totally reliable method can actually create a solution that looks real, but it's a fake. The official term is extraneous solution, but honestly, I just like to call them imposters.
This right here, this is the heart of the problem. We all know -2 does not equal +2. Obviously, that's a false statement. But look what happens when you square both sides. You get 4 equals 4, which is a true statement. The act of squaring completely erased that original negative sign. It's a process that can actually lose information. And in doing so, it can make something that was false suddenly appear true.
And that, my friends, is exactly what an extraneous solution is. It's a number you get by doing all the algebra perfectly right, but when you go to check it, it just doesn't work in the original equation. It's a total imposter, created by that very act of squaring.
Okay, time for a new case. Now this one looks simple enough on the surface, but it is a classic setup for an imposter to show up. See, when we square both sides here, we're going to end up with a quadratic equation, and those often give us 2 possible solutions.
So, after we square both sides and solve that quadratic, we're left with 2 suspects, x equals 4 and x equals 7. And as good detectives, it's our job to interrogate both of them and figure out which one, if any, is telling the truth.
And how do we interrogate them? With the check step, of course. This is where the truth always comes out. Sometimes a solution lines up perfectly, no problem. But other times, the whole thing just falls apart and it reveals the imposter. So let's see how our 2 suspects hold up under a little questioning. Okay, first up for interrogation, x equals 4.
Let's plug it in. On the left, we get the square root of 1, which is 1. Simple enough. But on the right, we get 4 minus 5, which is negative 1. Wait a minute. 1 does not equal negative 1. Busted. That is an imposter. Now for our other suspect, x equals 7. Plugging that in gives us the square root of 4, which is 2. And on the right, 7 minus 5 is also 2. It checks out perfectly. Case closed. The only real solution here is 7.
All right, so now we know how to spot an imposter. Let's level up and apply our skills to some more complex cases. I'm talking about the ones with more than one radical.
Now, when you first see an equation with 2 radicals, your first instinct might be to panic. Don't. The strategy is almost exactly the same. You just need to isolate one of them to start. So here, let's just add the square root of x to both sides. That'll get the square root of x plus 2 all by itself.
Okay, so we've isolated one. Now we square both sides. The left side is easy. That's just x plus 2. The right side is a binomial, so we got to be a little careful with our algebra. But look what happens. After all that work, there's still a radical in our equation.
So what do we do now? Simple. We just run the procedure again. No big deal. We isolate the radical that's left, we square both sides one more time, we solve whatever's left, and then, you guessed it, we check our answer.
And after we isolate that second radical and square everything one last time, all the algebra cleans up really nicely, and it leaves us with x equals 1/4. We do our final check, plugging it way back into the original equation, and it works out perfectly. This one is the real deal.
So we've investigated simple cases, we've unmasked imposter solutions, and we've tackled those tricky multi-radical problems. What's the final verdict? What's the big takeaway here?
It really all comes down to the detective's code. Rule 1, squaring both sides is your #1 tool for getting rid of radicals. Rule 2, you have to remember that this tool can create imposters, those pesky extraneous solutions. And Rule 3, the only way to catch an imposter is to check your work. Always, always, always check every single solution in the original equation. It's not optional. It's the last, most important step of any investigation.
And that kind of brings us to a final, bigger thought, right? We've just seen how a basic operation like squaring can literally create answers out of thin air that look right but are totally wrong. It really makes you wonder, what other imposters might be hiding in the math we do every day? What other processes might be leading us astray if we're not careful? Something to chew on. Thanks for cracking this case with me.